Welcome back. Hopefully you're joining us after viewing part 1 of this video series. If you have not watched part 1, you probably want to stop right now and go back and watch part 1 because you don't have much chance of starting part 2 cold and getting caught up at all. Students, I just realized that I had a mistake in my spreadsheet. In this formula, I had B21 instead of B22. And when I corrected that just now, what you probably saw on the screen was some of the values of y and consequently the delta changed. Just know that I did make a correction, but it's not going to affect us as we go through this because now it's correct and we're going to just keep walking through this step by step. So let's do the second iteration. We take as inputs x1 and x2. We know that the output of that should be a 1 because our comparison is if x1 or x2 is true or a 1, we evaluate as 1. We feed those into our weighted sum function with the weights 0.1 and 0.3. Here's our weighted sum function. Our outcome is 0.3. Because that 0.3 is not greater than our threshold value of 0.5, we evaluate that as a 0. But when we make our comparison to calculate our error, we know that our guess is not the same as what we expected, so we have an error of 0. And in this case, now this depends on the algorithm that you want to use. Each algorithm would be different. This algorithm is going to increment the weight for variable 2, and they're going to increment it by the alpha. So you see it the weight for variable 2 goes from 0.3 to 0.5. That's because the algorithm is saying we'll increment one of the weights. It does not increment both weights at the same time. It'll only do one or the other. The specific algorithm said to increment weight 2. You'll notice that the reason that we increment the weight is because we have an error. Up here where we didn't have any error, our weights stay the same. We started with 0.1 and 0.3, we end with 0.1 and 0.3. Down here we have a 0.1 and 0.3, but because we have an error we've incremented, we end up with 0.1 and 0.5. Let's do a third iteration through the algorithm, and that means we're looking at row 6 in this case. In row 6, our inputs, this time we swapped the 0 and 1 that we had in row 5. That was iteration 2 for a 1 and a 0. So the input for x1 is 1. Its weight in this case is 0.1. The input for variable 2 is 0. Its weight is now 0.5. That's because in the last iteration we incremented because we had an error. Our weighted sum, here's the function and here's the value. It's 0.1. Again, we compare our 0.1 to our threshold value, which we set at 0.5. Our rule is if our weighted sum is greater than our threshold value, we assign a 1. It is not greater than our threshold value, so we assign a 0. Our error is a 1 because in reality we should have gotten a 1. Our algorithm this time told us that our weighted sum evaluated to a 0, so we were incorrect. And because we were incorrect, we're going to change our weights. We're going to change the weight by our alpha of 0.2. In the previous iteration, we changed weight 2. In this iteration, then, we're going to change weight 1. So the algorithm in this case tells us to go back and forth. Let's go ahead and do iteration 4. Iteration 4 is in row 7. The inputs in this case are 1 and 1. Their weights are 0.3 and 0.5. Here's the formula, and here's the outcome of our weighted sum formula. It's 0.8. This is our calculated or our weighted sum. It's 0.8. We compare it then to our threshold of 0.5. It is greater than our threshold, so the action that we want to take this time is assign a value of 1. When we compare our estimated or our guess or what the algorithm told us to assign to what we know should be true, they match. So our error this time is a 0, and we're very happy to see that. And we also don't change our weights. Our error was 0, so we don't change our weights. This time, now we just ran through all 4 examples that we have. We're going to start to go through them again. You'll notice the values are the same. We've already run through these values, but their weights are different. The algorithm is still learning at this point. So we take our values of 0 and 0. We've done these before, but their weights were 0.1 and 0.3. We're now going to run those same values, 0 and 0, but with weights of 0.3 and 0.5. When we run those through the weighted sum function, we end up with a 0. We said our 0 does not meet the threshold value of 0.5. We're going to assign that then an outcome or a guessed outcome or an estimated outcome of 0. In this case, oh, sorry, I'm on the wrong one there. I'm going to compare that to my actual value, which was 0. I say, great, I don't have an error. I'm going to keep those weights the same. Let's go one more iteration to iteration. This should be 6. I have a 0 and a 1 as inputs. Their weights are 0.3 and 0.5. Their weighted sum is 0.5. I compare that to my threshold. It's exactly my threshold, but my rule is it has to be greater than the threshold, so I'm going to assign that as a 0. My calculated 0 and my actual value of 1 are different, so I have an error. And again, in this case, since I do have an error, I'm going to increment by the value of alpha. I've been going back and forth, and this time it's weight 2's turn to get incremented. At this point, we have walked through 6 iterations, and hopefully you understand how this process works. You would then iterate. You'd come down, and as you walk through those data points a 4th time, now with weights of 0.7, you'll see that for every guess or assessment that the computer makes, it actually is correct every time. It has a delta or an error of 0. Now, that's not going to happen if you have a situation where your neural network has 0 error. You probably have a ridiculously simple problem that you don't need a neural network for. What you would have specified is, well, I need an error of a certain amount. That's where we talk about things like sensitivity, specificity, type 1 error, type 2 error, those types of things. But you can see that the algorithm has ended up with an acceptable weight, and as long as you use those weights to make your evaluations, you should be able to get a very good or very low error rate. Now, question that I know you're asking is, actually, wouldn't a better weight have been 0.51 instead of 0.7? Yes, that's true, but to get to that 0.51, or you could say just a 0.6 would have been lower than 0.7. I could have got there and it would have been just as good as a 0.7. Yes, a 0.51 or a 0.6 would have worked just as well as a 0.7 as a rule. However, the point here is it would have taken much longer. We got this whole rule worked out with 0 errors in 16 iterations. If we wanted to end up with a more accurate threshold, such as 0.6, it would have taken us a lot more iterations. And if we wanted to get to a 0.51, that means that our alpha would have been a 0.01. We would have gone from 0.51 to 0.52 to 0.53. We would have gone through this dozens, really scores of times. And when you get a big data set, you would have been going through this 10 or 20, maybe 50 times more than you did here. So if you have read the book, you understand what they're saying when they tell you that the bigger the alpha, the faster the algorithm will learn. I just have a few seconds left before we hit the end of the YouTube 10-minute limit. I just want to remind you, this is only one algorithm. There are lots and lots of algorithms. They're discussed in the subsequent sections of your book, and I hope you learned something and maybe actually enjoyed the exercise. Have a good day.